Hello, everyone. My name is Jianyu Chen. I'm from Delft University of Technology. Today, I'm going to give a presentation about our work, a matrix multiply unit for posits in reconfigurable logic using Open CAPI. This is the content of my presentation today. First, I will introduce the motivation of this project. And then I will introduce the matrix multiply unit. And after that, I will introduce the multiply-accumulator with the quire registers. Well, and finally, I will say something about the performance on CAPI 1.0 interface. Well, first, the motivation of this project. When I began to do this project, there is only software implementation of the posit, which is pretty slow. And well, there is no posit multiply accumulator with quire registers. Well, this is the way introduced a decade ago, and it's recommended by Mr. John Gustafson in his paper. Well, as we know, when we have the fused multiply adder to delay the rounding, first do the multiply and do the addition, and after that do the rounding, which can make the calculation more accurate. And a similar idea can be applied for the multiply accumulator. First, do the multiply and all the accumulation, and only do the rounding after all the accumulation, which can increase the calculation accuracy. And well, we choose to design a matrix multiply because we think this kind of hardware can speed up the calculation. And finally, we get a speed up of more than 1,000 times. Well, first, let's say something about the CAPI 1.0 interface. This is the interface to connect some customer accelerator engine to the IBM Power 8 computer. Well, the custom accelerator engine can be FPGA or GPU or ASIC, and in this project, I use FPGA. Well, I choose to use this interface because it's it's a very efficient interface. Well, only the pointer of the data will be passed from CPU to FPGA. Well, but in practice, sometimes in order to make the implementation more easier, so what we passed from the CPU to FPGA is more than the pointer of the data. For example, in my implementation, I passed the pointer of the data and the size of the matrix to the FPGA. And then FPGA can read the data from the memory itself and do the calculation. And finally, it can put the data back to the memory, and the CPU can use it. Well, and another reason to use it is its API is pretty simple. It's pretty easy to do the programming on it. Yes, in my design works on the 32-bit posit number with ES equal to 2. And well, it can use the FPGA to do the multiplication of two matrices. Well, it can do the calculation more accurate than the traditional one. Well, this is the diagram of the matrix multiply unit. As you can see, first, it's a unit to calculate the C times A and C times, to calculate matrix A times matrix B. Well, in the beginning, all the data will be loaded in the RAM A and the RAM B, the matrix A to the RAM A and the matrix B to the RAM B. And as you can see, there are 64 multiply accumulator units. The data, it can get the data from these two RAM and do the calculation. And the result of the calculation will be first stored in the RAM C and sent back. Well, as you can see here, the output of the RAM A is 32-bit, and the it's one positive number, and the output of the RAM B is 64 positive number. There are 64 multiply accumulator units inside, so which means 64 numbers in the result can be calculated at the same time. It's much faster. And now I will introduce the multiply-accumulator unit here. Well, before doing the calculation, I need to do some transformation on the positive number. Well, I will calculate exponent value based on the regime bit and the exponent bit. The exponent value will be an 8-bit number. It's very easy to do the transformation. First, I just copy the first bit of the regime bit to the bit 7, and then I apply leading zero counter to the positive number. If the bit 7 is equals to 0, it will inverse the result and put it here. And if this bit is equal to 1, it will simply put the result here. And the last step is to copy the exponent bit to bit 0 and bit 1. After this kind of transformation, the format of the number will become like this. And now I will do the calculation based on this kind of format. Well, let's introduce a multiply-accumulator with square registers. This kind of multiply-accumulator will maintain a 512-bit accuracy and of the immediate result, which means it will only do the rounding after all the accumulation. Well, it's more accurate than the traditional one. For example, if I calculate A plus B minus A, the result will always be B, even if the number A is much greater than B. And in my implementation, I use 512-bit to present 2 to the power 200 and 2 to the power minus 255 to 2 to the power 256. But in practice, we don't need to use 512-bit. But in my design, in order to make the implementation easier, I choose to use this number. Well, but if I implement it directly, the performance will be pretty low because doing the addition and the normalization for 512-bit number is very expensive and slow. So I get some idea to improve it. First, I cut the 512-bit number into some 64-bit blocks, which means there will be 8 this kind of blocks. And then for each 64-bit blocks, I append an extra 16-bit for the carry on its left, and the carry generated in this block will be saved in the carry block here. So it's a kind of carry safe adder, but different from the normal one. Well, if I do a multiplication for 2 positive numbers, the result will be a 56-bit fractions. And if I add this fraction to the quire registers, only 1 or 2 blocks will be influenced. So first I cut it into 2 parts, and then I add 2 parts of the fraction into 2 adjacent blocks. And if some carry happened in this process, the carry will be saved in the carry block. It will not be processed immediately. Well, and after all the accumulation, I need to do the carry. Well, after the carry, the pattern will be if the result is positive, the pattern of the result will be like this. And but in practice, only 2 blocks are used to do the normalization. The block with the leading one and its neighboring right block. Only these 2 blocks are useful to do the normalization. So in the normalization, first we need to pick these 2 blocks out. But in practice, we can doing this process while doing the carry. So we can do these 2 things at the same time to save time. If the result is negative, the pattern will be similar but a little bit different. So only the block with the leading 0 and its neighboring right block are useful. Well, in order to keep a high throughput, I put 2 RAMs in the multiply-accumulator unit. Well, each RAM is a quire register. So which means in the multiply-accumulator there are 2 quire registers, and the carry safe adder block and the carry block. These 2 blocks will take turns to use these 2 quire registers. This is a diagram of the operation. In the beginning, the carry safe adder will process the data and add numbers to the RAM 1. This is the first quire registers. While at the same time, the carry block can do the carry for the RAM 2, the other quire registers. And after all the addition is done, there will be a shift of the state, and the carry safe adder will add numbers to the second quire registers. Well, at the same time, the carry block will do the carry for the first quire registers. This kind of double buffering structure can make sure our design can always process the input data, make it more efficient. And we get a new word, GPOP. It means gigaposit operation per second. It seems that Mr. John Gustafsson likes it, so we use it. And our design can achieve 16 GPOP when do the multiplication for two 128 times 128 matrices. Well, it's already more than 1,000 times faster than the software implementation. And the device of CAPI 1.0 is available on the TEC, Texas Advanced Computing Center. Every researcher can apply an account and use it for free. And the design of matrix multiply units is open source, and it's available on GitHub. This is my GitHub address. So let's draw a conclusion. We developed a kind of hardware posit, and it can do the calculation for 16 GPOP. It's 1,000 times speed up. And it's open source in the GitHub, and everyone can use it for free on the TEC. And our future plan is to move it on the Open CAPI interface. It's a new kind of CAPI interface. It's faster and it's more flexible. And from our estimation, the speed of calculation can be 64 GPOP in theory. And that's all. Thank you.
Okay, thank you very much. And we have a few minutes for questions. Really interesting. There are a couple. Let's start with you. Okay.
Two questions. So what was the FPGA that you actually used, and what frequency did your design run at?
I used a Xilinx FPGA, and the frequency of my design is 250 megahertz.
And what Xilinx FPGA do you remember?
Sorry, I didn't remember that, but later I can show you later. Okay. Okay.
Okay, thank you. There was another question from the back.
So you seem to be on the carry propagation side. So you seem to be storing the carry in a lookup table, right?
What?
Are you storing the carry propagation?
Yeah.
Carry,
Yeah.
in a RAM. What is the RAM size?
Let me. Each RAM should be enough to store the bandwidth of the RAM. It's a distributed. It's not a block RAM. It's a distributed RAM, and the bandwidth of the RAM is 18-bit, and the depth of the RAM of each RAM is 4.
How do you index that RAM?
Well, because each time we need to access two blocks. So here I type RAM 1 and RAM 2, but in practice, RAM 1 consists of two distributed RAM. So we can access two adjacent blocks at the same time. here I only draw one RAM, but in practice it's two distributed RAMs.
Yeah, another one?
I have a leading question. Can you handle arrays larger than 128 by 128?
Yeah, in theory it's possible, but now because due to the limit of the size of the RAM, it can process 128 times 128. But in theory, it's possible to first load some of the matrix, do the calculation, and load the other part of the matrix. In theory, it's possible.
What will be the trick that gets you to 64 gigapops, your next generation?
Oh, well, here. Oh, sorry. Here we have 64 matrix multiply units because due to the limit of the throughput, so it's not that useful to add some more. But if we use open CAPI interface, we can have more multiply accumulator units here, which can increase the speed.
Question anymore? Anyone? Okay, thank you so much. And we're concluding the session. So.
Okay, thank you.